All right, welcome everybody. Thank you, Professor Headrick. Thank you so much for being here, being with us and giving us a talk. I just want to quickly introduce you. So Professor Headrick is a professor at Brandeis University. We know each other from there when I was a professor there too. He's been there for 16 years. And before that, he was a postdoc at MIT and Stanford, and he got his PhD in 2003 at Harvard University. And he's been doing research in string theory and quantum field theory. Is that right, or anything else?
Yeah.
No, that's okay, good. So we are super happy that you are here. The kids are super excited. They really wanted to know about string theory. They've been asking me a lot of questions, and I told them that I'm going to bring an expert in the field so they can talk to them. So yeah, take it away, please.
Okay, great. Thanks so much, Azadeh, for inviting me. I love talking about physics and string theory. So as I mentioned before, you should feel free if I'm saying something that doesn't make sense or I'm using a word, sometimes I might use a word that you don't know what it means because I haven't explained it. Just stop me and I'll try to explain it better. So um and also since of course I don't know you guys and I don't know exactly what you know already, I might also explain some things that you already know or not explain some things you don't know. So let's just keep it as a conversation so it's interesting for all of us. So yeah, I love so yeah, thanks again for inviting me. I love talking about physics and string theory and everything, which is what I do for my job. Um, so I thought maybe to begin, just to sort of give some context, I would just start by explaining where a person like me, a physicist like me, fits, among scientists, and what kinds of work I do, because, most scientists specialize in some very specific thing, and I'm no exception. So what kind of work do I do, and what kinds of questions do I try to answer in my work? So I'll just do like a classification, like a taxonomy, like you have of species, kingdom, phylum, class, and all of that stuff. So at the very top, oh, by the way, if you can't read my handwriting or I'm writing too small or too big, please let me know. Um, so we just have scientists. Okay, but that of course includes like a lot of different kinds of scientists. You've got your biologists, your chemists, um, your neuroscientists, your geologists, and so on. So within that, I do physics. Not going to try to define what is physics, what is not physics. But within physics, of course, there's a lot of different kinds of physicists who study different things. And roughly speaking, we kind of organize ourselves according to the size of the things that we study. So you have, at the biggest scales, you have physicists who study the whole universe. So those are the cosmologists. Then you have physicists who study like stars. So those are astrophysicists. And then you have physicists who study the Earth and things going on the Earth, the geophysicists. Then you have physicists who study matter. So like, glass and metals, superconductors and stuff like that. Those are the condensed matter physicists. Then you get smaller and you get the atomic physicists. And then even smaller, the nuclear physicists who study atomic nuclei. But that's not small enough for me. So my group of physicists are, so here we have all the different kinds of physicists. I'm not going to write them all out. The particle physicists who study the smallest things of all, which are particles, which is by definition just whatever the smallest thing is that you can observe or do an experiment with. Okay, so examples of these are what are sometimes called elementary particles or subatomic particles. Maybe, I don't know, can one of you give me an example of a kind of a particle? Rex?
Quarks.
Quarks,
If you,
awesome, love
if you
it.
need something more specific, the charm quark.
The charm quark, a very specific quark. Great. So we've got our quarks. We've got electrons,
Sirish wants to
neutrinos,
add.
photons. What was that?
Sirish wants to add something.
Yeah,
Yes,
I
let's hear
have
it.
all the leptons.
The leptons. That's a group of particles that includes the electrons and the neutrinos.
So, Soren, go ahead.
Strings.
Strings, he said.
Oh, okay, we're not there. We're going to get to the strings. We're going to get to the
Yay.
strings.
Nice.
You're jumping ahead there.
Rex
So,
wants to add something too.
Actually,
Yeah.
I wanted to say that quantum strings are topological defects, not particles.
okay, all right.
Yeah,
Okay.
they're not quantum strings are the topological defects made from when the universe began that still persist today.
Right.
Oh, cosmic strings, yes.
Yeah.
Yeah, there's a theory about that. They haven't been seen yet, but there's different kinds of strings. So we'll get to that in a minute. Okay, so there's like a pretty big group of physicists who call themselves particle physicists, but among the particle physicists, there's two completely separate groups. Okay. On the one hand, we have the people that I'm not, and that's the experimentalists. And the experimentalists are the ones who actually obviously do the experiments. And what kinds of experiments? Well, at colliders, like particle colliders, like one you might have heard of called the LHC, the Large Hadron Collider in Switzerland, where they smash protons together at very, very high energies and see all kinds of particles coming off. So they study the interactions of these particles and they make cool particles like the Higgs boson that you've probably heard of and so on. And there's other particle experimentalists who observe neutrinos. They have huge observatories like in Antarctica where they use the ice of Antarctica to observe neutrinos coming from the universe, et cetera. So there's different experiments that the experimentalists do. And the experimentalists are people who build machines and these are generally huge machines or huge, very complicated experiments with thousands of people working on them, building them, and so on. And they're very, very good at kind of making things and actually, studying the real world. And that is not what I am at all. So the other species, if we're down to the species level here, is the theorists. So that's what I do. So theory means just trying to understand the theories that govern the laws of nature that govern these particles and how they interact with each other and so on. And you really need a group of people who are trained just in that because it's because the work that you do requires a lot of very specialized knowledge, just like it requires a lot of very specialized knowledge to create an experiment in physics. Understanding the theories also requires a lot of specialized knowledge, and a lot of that knowledge is basically mathematical knowledge. Now, you might think I'm done here, but I'm not, because within the theory people, there's still two different subspecies. Now we're getting into the real specifics, but it's an important distinction. You have the ones who...
It's supposed to be on there. Why does leave a meaning thing still on there?
Don't touch it or you'll leave the meeting.
Why are the things still on there?
I don't know why.
Should I keep going, Azadeh? Okay. So among the theorists, and I'm a theorist, there's the ones who work with the experimentalists. So, and what they do is they try to predict the results of experiments. Well, first of all, they try to propose experiments that they think will be useful for understanding the laws of nature. They predict the results of experiments. They analyze the results of experiments and so on, and they correct their theories if the theory is not making a prediction that agrees with what the experiment shows, et cetera. And those people, there's a not very helpful name for them, which I'll write down, but it's not anything you need to know or remember, I think. So we call those the pheno people. Pheno is short for phenomenon because they actually think about the actual phenomena and they talk to the experimentalists a lot. And again, that is not what I am. I need a different color for myself, something more exciting. So I'm a string theorist. So that's when you really get down to this bottom level. And the string theorists are asking more fundamental questions and asking questions about the laws of nature that are not yet, that we cannot yet directly answer by experiment. And so we're thinking about very, very basic and fundamental questions about the nature of the universe, about space and time, and so on. And since we do not have experiment to directly guide us, we rely on what we know about physical theories and the math, basically. And so what I do on a day-to-day basis is just basically work through math problems that are suggested by these basic questions, which is what I'm going to talk about in the rest of this meeting. What kinds of questions and what, how do we answer them and so on. But let me just say that, in the whole world, there's maybe, a few thousand string theorists. I mean, by the time you get all the way down, all the way down from here, all the way down to here, it's a very specialized group. There's a few thousand of us in the world. And we, mostly kind of know each other, and we talk to each other at meetings. I'm at a meeting right now. Where I'm talking to other string theorists and so on, and we work together a lot. And the work that we do is basically math problems. It's just scribbling equations on blackboards, and sometimes using a computer, running a computer program or something like that. So I see at least a couple people have hands up, so maybe I'll just stop talking and listen for what questions there might be. Should I call on someone, or Azza, did you want to call on someone?
I think Rex's hand was up from before. Luke, do you have a question?
I think you're muted there.
Luca, do you have a question? I said Luke, sorry.
What does he mean by like thousands of string theories?
Oh, what do you mean by only 1,000 string theorists?
Yeah, so
Right. Go ahead, sorry.
yeah,
Right.
if you look at all the scientists, all around the world, there are scientists doing all kinds of different interesting kinds of science. If you just look at the ones who do the kind of science that I do, which is what I'll explain, they're working all over the world, but if you just count us, there's maybe 10,000 of us, or I don't actually know the exact number, but it's compared to all of the scientists doing all kinds of other different kinds of science, it's actually a fairly small number. Yeah.
Sirish has a question. Let's just see what Sirish has to say. Go ahead.
So what kind of math do you typically use the most, and like what level?
Yeah, that's a great question. So we use all kinds of math. There's a lot of geometry. There's a lot of differential equations, a lot of algebra, and really most kinds of math we use in one way or another. And in fact, what very often happens in this kind of work is that there are math questions that the mathematicians don't know the answers to, and so we have to figure it out ourselves. And so what we actually end up doing is developing new math to help us solve the problems that we want to answer. So we're actually right, really at the frontiers of math knowledge. And in the day-to-day work, it's really, trying to, for example, prove a theorem that, there's a conjecture, we think it's true, and we try to prove it, or do a new kind of calculation, figure out a new way to calculate some quantity. So we're all the time trying to invent new math. And for me, that's actually, I went into this partly because I love doing math, and I'm constantly having to learn math. So either, pick up a textbook on some kind of math that I didn't know anything about, or just invent it myself if there's no textbook on it yet. So, yeah. So maybe I can start talking a little bit about what is string theory and why does it exist, and what are we trying to accomplish with it? So I said that we we're trying to answer very, very fundamental questions, and the thing is that we get to use a lot of imagination because there are just some very basic things that we don't understand yet about the fundamental laws of nature. And so just to give you an example of the kind of thing that goes on in my field, we often imagine different universes. So, as I'm sure you've learned in Azade's class, when you have a tough physics problem, one thing you can often do, and that's the thing that a physicist will often do, is just to try to simplify it, right? So, so if you're talking about, some problem involving a car driving down the road, it's a physics problem, you're not necessarily going to have every single detail of what the car is doing and, what every molecule in the car is doing. No, you just simplify. You say a car is moving down the road at 60 miles an hour or is accelerating or whatever, so you just simplify it. And so we do that with the universe. So we say sometimes some problems are easier if you change the number of dimensions of space, for example. So this is something we do all the time. So we say, imagine that instead of space being 3-dimensional, imagine it was just 2-dimensional. And then maybe space is like a plane, or maybe it's a sphere, or maybe it has the shape of a donut, torus, or maybe it's just 1-dimensional, or maybe it's just 0-dimensional. Maybe you have a universe which is just a particle. And that usually makes things much easier to, if you have a universe which is just a particle, but often you can, calculate things, understand things a lot better. But in fact, or sometimes we go to more dimensions. So it turns out that some things get simpler when you imagine space is 4-dimensional or 5-dimensional. And in fact, at some point, what you do is you just say, well, maybe the number of dimensions of space is itself a variable. Okay, so so when you guys do physics with Azadeh, you have variables like the position of something or the amount of time it takes for a car to move from here to there or something like that. So you have these variables like position, time, and so on. So we often add a variable which is the number of dimensions. Whoops. So the number of dimensions of space, and we can call that D. Okay, and then we just consider that to be a variable. Now, you might say, okay, what kind of equation would the number of dimensions of space appear in? So I can give you a couple of, a math example and a physics example. So a math example would be if you wanted to know the amount of space in a square of a given size. So if I have a square whose side length is L, if it's really a square, then I'm in 2 dimensions. And what's the area? I know this question is too easy for you guys, but I'll ask it anyway. What's the area of this square? Rex, go ahead.
L squared.
L squared. What if I'll just ask you, Rex, so what if it had been a cube?
L cubed.
L cubed. So what do you think it is if I'm just in D dimensions?
L to the D.
L to the D. Okay, so that's a fairly simple example. So the amount of space within a square or a cube of a given length is L to the D. So now we have a quantity that has 2 variables, L and D. Okay, here's another example, which is actually a physics example. So Newton's law of gravitation. Have you guys studied that? Yes,
have.
I'm seeing people nodding. Okay, so that tells me the force of gravity if I have 2 objects. Let's say one of them has mass big M and the other one has mass little m, and the force of attraction between them is what, according to Newton? Somebody other than Rex. We've already heard from Rex.
Sirish, go ahead.
Yeah, so it's g, the constant of for gravity, and then it's the first mass times the second mass, and that's all over the square of the radius, the distance between them.
Right, so we have some distance r between them. Sorry, it's a little messy there. Now, this 2 here is because you're in 3 dimensions of space. And it turns out the general rule in any number of dimensions is just r to the d minus 1. So if you're in a 2-dimensional, if the universe was only 2-dimensional, Newton's law would say that the force of attraction was 1 over the distance, not 1 over the distance squared. If the universe was 4-dimensional, had 4 dimensions of space, it would be 1 over the distance cubed. Okay, so then you can just go ahead in whatever problem you're trying to solve, you can just leave this d, as a variable, instead of fixing to d equals 3. Okay, so this is something we do all the time. Just consider the number of dimensions of space to be this variable that can just like in this equation, you don't necessarily have to know what little m is. You write the equation, works for any little m. We write the equation, it works for any dimension d, stuff like that. Okay, so now what is an example of the kind of fundamental question that we're trying to solve in string theory, and what does this name string come from? Well, basically, one of the questions we're trying to answer in this field is a very fundamental question. Whoops, that didn't work. So which is how to make a theory that combines quantum mechanics and gravity. Okay, so we have these 2 things, quantum mechanics and gravity. Well, these are both facts about the world that we've known. In each case, well, quantum mechanics we've known about for about 100 years. In fact, 2025, the UN has declared is the World International Year of the Quantum, because it was 100 years ago in 1925, 100 years ago next year, that quantum mechanics was really finally understood by physicists. So we've had 100 years to understand quantum mechanics, and I'll say a few words about what it is and how it changes our view of the world. And then, of course, we have gravity, which has been known much longer than quantum mechanics. And obviously, since the beginning of time, people have known about gravity. But the first good theory of gravity was Newton's theory, 400 years ago. But that's not the modern theory of gravity. So Newton's theory is this one that we just talked about, and it's an excellent theory. It works well for almost every everyday purpose or engineering purpose. But we have a better, more modern theory of gravity, which is Einstein's general theory of relativity. So let me just write that in here. So plus general relativity. And I'll say a few words about what that is. But basically, that is our modern theory of gravity. And it's also about 100 years old, a little bit more. It was developed by Einstein in the 1910s. So, so these are 2 very, very, very good theories that we use all the time in physics. We know that both of them are excellent theories. They describe a whole lot of phenomena. We don't know of a single experiment that disagrees with the predictions of quantum mechanics. We don't know of a single experiment that's ever been done or observation that disagrees with the predictions of general relativity. But the thing is, we also don't know a single experiment or observation where you would need both of these theories at once to predict the outcome. And these theories are not actually compatible with each other. And so this is like a great theoretical puzzle, right? It's not an experimental puzzle because there's no experiment that's actually been done where we don't know how to predict the outcome, because every experiment that's been done in physics, either you would use quantum mechanics to predict the outcome and quantum mechanics works, or you would use general relativity to predict the outcome and general relativity works, and you say, yay, I've got this, I've covered it all. But the thing is that the two theories themselves are not actually compatible with each other. Okay. And so that leaves as a job for the theorist to figure out what the heck is going on. Okay.
Could you give
and
us an example of why they're incompatible or in what situation they're
yes,
incompatible? Thank you.
yes. So that's what I'm getting to next. Thank you. Let me say a couple of quick words about general relativity, which I think you guys have probably heard of, and maybe some of you have watched YouTube videos on or something, but I still think it's helpful to to remind us of what it is. So, Einstein's insight in developing general relativity was that gravity is not like a force like other forces, that it's what's called a fictitious force. So a fictitious force is a force that's because your reference frame is actually accelerating. So like if you're in a car and the car starts accelerating, you feel a force which pushes you against your seat back. Well, there wasn't actually anything pushing you against your seat back. It's actually your seat back was pushing against you to get you to accelerate. And you experience that as a force that's pushing you back. Or if the person hits the brakes and then you feel this force which is pushing you forward. Okay, or if they steer to the left, suddenly you feel a force which is pushing you to the right. And that's the centrifugal force. So those are all fictitious forces. And Einstein said that gravity is a fictitious force, so that actually if I drop my pencil, and we learn in physics class that the pencil is attracted by the earth and it's accelerating downwards. Somebody remind me what is the acceleration downwards for my pencil if I drop it? Sirish.
Around 9.8 meters per second.
Per second?
Squared.
Squared. Okay, so Einstein said that that's nonsense. Thank you, Sirish. That's nonsense, that in fact, you're just in an accelerating reference frame. The room I'm sitting in fact, the world around, because I can look out the window, is actually accelerating upwards at 9.8 meters per second squared. And it's just a fictitious force that I feel like I'm being pulled down because everything is just accelerating upward. And at first, that's total nonsense, because if, I'm here in Colorado, and if the surface of the earth, I mean, is Colorado accelerating away from the center of the earth at 9.8 meters per second squared? That's ridiculous. The distance between Colorado and the center of the earth has not changed. Okay, it's whatever, it's whatever it was. There's no acceleration going on. So it seems like a contradiction, which Einstein eventually resolved by saying that actually the contradiction is resolved by the fact that space-time itself has some curvature. And anytime you have some curvature in space or in space-time, the whole idea of accelerating or turning versus going straight becomes confusing. And that confusion actually resolves the paradox. So let me just give a quick example that you're, from somewhat everyday life, if you fly on planes and go places. So here I have a model of the Earth. Okay, is this visible, Azadeh? Can people see what I'm showing? Okay, so.
Yes, we can see.
So we're gonna take a trip on the Earth. So here I have, let's say you're flying, you guys, a lot of you are in New Jersey, right? So this is New York.
We have some from Australia actually in this group.
Okay, so maybe
It's
we'll
all over.
fly.
It's international.
It's international. Okay, so there's New York, and we're gonna fly from New York to Paris. Okay, and so there's Paris, there's New York. I didn't mark the North Pole and the South Pole. I didn't draw the continents. Sorry about that. But anyway, the pilot is going to fly, I mean, they're just going to go straight, right? Basically, so they just go straight from New York to Paris. Okay. Now, if you're sitting in the plane that's flying from New York to Paris, you'll often see a map that looks like this, like on the seat in front of you. So here's a world map. You guys see the world map? And New York is like, okay, I just drew with a marker on my iPad. It was inevitable that that was going to happen. Okay. Whoops. Okay. Here's New York. And here's Paris. And if you look at the flight trajectory from New York to Paris, I guarantee you it will look like this. Okay. The pilot will go north towards the North Pole and then south again. Why did they do that? Why didn't they just, go straight? Well, the thing is that this one that looks straight on the map, if I do it on the globe, being careful to use the marker for the globe and the pencil for the iPad, it would actually look like this. So it would look like, I don't know if you guys can see that.
It just tilted down a little bit.
Oh,
Yeah.
there we go. It would look like the pilot went out of his way. Okay, so this is the trajectory where there's no curvature, but it looks, when you draw it this way, like there is curvature. And the dotted one, it looks like there's no curvature, but there really is. And that's exactly the same as the acceleration versus no acceleration when I drop the pencil. So the pencil, when I drop it, as it's falling, it's actually not accelerating. That's this straight line here, but it feels like it is accelerating, whereas the pencil that's just sitting in my hand seems like it's not accelerating, but actually it is accelerating upwards at 9.8 meters per squared, and that's like the dotted line. And the only way that this whole thing makes any sense is because the space-time itself, the only reason this is not obviously wrong is because the space-time itself is curved. Okay, and it's not just the space, by the way. So the surface of the Earth, it's just the space that's curved, but in general relativity, it's the space-time that's curved. Space-time being this four-dimensional space that has 3 dimensions of space and 1 dimension of time, and the whole thing together has a curvature to it. Okay, so the thing and why is it curved? Well, it's curved because there's some mass. It's the mass of the Earth that's creating that curvature. And so what you have in general relativity is this new idea, which is that the geometry of space-time itself is physical, meaning it's dynamical, meaning it changes depending on what's going on, what masses there are, and how the masses are moving. So it's a thing itself, whereas in Newtonian physics, you've got space, you've got time, and they're just sitting there. They're not doing anything. They don't react to what's going on in the universe. They're just there eternally. Okay, so the new idea in general relativity is that the geometry of space-time, the curvature of space-time, is itself a physical thing that responds to matter, to things moving around, and so on. And in fact, it can have its own dynamics. As an example, there are what are called gravitational waves that are emitted by, so that the things with the strongest gravity in the universe are black holes. And when black holes orbit each other or collide, they send out these waves. What are the waves in? They're not light waves, they're not sound waves. They're waves in the geometry of space-time itself that go across the universe. And for the first time were observed in 2015 by what are called gravitational wave observatories. Like you may have heard of one called LIGO, for example. Okay, so so that's the lesson. So let me write this down. So in GR being general relativity, space-time, geometry. This is why we use a lot of geometry, is physical. Okay, so it's a thing itself. It has it stores energy. You can send energy from one place to another, and all of this stuff. Okay, just the same way light waves, go from one place in the universe to another, and sound waves and so on. So it's a thing itself, and that's actually what causes all of the problems. So on the one hand, general relativity is an amazing theory that all of the observations that have been done of the universe, of black holes, of galaxies, work perfectly with general relativity. Okay, not one experiment or observation has been made that contradicts the predictions. But this fact that it is physical means that when you combine it with quantum mechanics, you get trouble. And where do you get the trouble? Well, you get trouble from the fact that in quantum mechanics, you have something called uncertainty. Okay. So quantum mechanics, you have uncertainty. What does this mean? So it means basically that physical variables like positions, speeds, velocities, forces, all of these things do not have definite values in quantum mechanics. So it's much more complicated because actually they're fuzzy. They have distributions of values. Okay. So an example is in an atom, like a hydrogen atom, the electron is orbiting the proton. So here we've got the proton, and we've got an electron that's just orbiting like the Earth orbits the sun, going around in a circle. This is not true. Okay, because in quantum mechanics, actually, that electron actually has a very fuzzy position. Okay, and the size of the atom is the extent of that fuzziness. Okay, and all of the behavior you have of atoms, like making molecules and everything, is because of the quantum mechanics and that fuzziness of the electron position. Okay, maybe I've been talking for a long time. Let me just take a brief pause and ask if there's any questions before I explain why it's a problem to combine quantum mechanics and general relativity.
Yeah, so these guys have had quantum mechanics. They know about uncertainty, and they're very versed in everything chemistry related.
Okay.
So you guys have any questions so far? Let's see. Doesn't look like there's any.
Okay.
So we have done like Fourier addition, Fourier series and everything. So they have seen the distribution, position distribution versus the momentum distribution. So they know about uncertainty. So you can.
Okay. Awesome. But I think Sirish has a question, right?
Yeah, okay, Sirish, go ahead. Sorry.
When we're talking about the size, is that like to a certain probability, the actual size that defined?
Wait, say that again?
So when we're talking about the size, is it the chance that the electrons will be there up to a certain extent, like a certain limit probability for the size?
Yeah. I mean, right. So I mean, as I guess since you've studied it, in the case of an electron orbital in an atom, it's never 100%. I mean, in principle, the electron orbital goes out infinitely far, but it goes to zero very, very quickly past some distance. And for the hydrogen atom, that distance is called the Bohr radius. It's about half an angstrom. And past this distance, so there isn't like a strict wall around the hydrogen atom, but past that distance, it's almost a vanishing probability of finding the electron. There are other situations where you have where the distribution is really much more spread out. Like, for example, an electron moving in a metal or a conductor. Those things have probabilities that are really spread out on almost the whole piece of metal, actually. The ones that are carrying the current, the conduction electrons are very, very delocalized. So anyway, there's a lot of different things that weird and wonderful things that happen in the world of quantum mechanics. Yeah, go ahead. Did not get that. Can you repeat it?
Or maybe write it in the chat. We can't hear you very well. If you could write it in the chat, that would be good.
Oh, there's a lot of things in the chat.
Yeah, but those are kind of, they're talking to themselves.
Oh, okay, that's fine.
They answered your questions. There's a lot of answering questions in the chat. So that's.
Oh, cool. Okay. Awesome. Awesome.
Yeah, you can keep going on.
Okay. All right. So, so the problem with this uncertainty is that it includes even the geometry of space-time. And that means that the geometry of space-time is itself a little bit uncertain. It's kind of, you know, fluctuating or vibrating. Okay. So we perceive space, you know, to be smooth, to be nice and smooth. We don't notice any bumpiness or fluctuations in space-time. But that's because we haven't looked close enough, basically. So you can actually calculate how big these, if you just take quantum mechanics and take general relativity and put them together, you can just figure out how big these fluctuations are. And you get an answer that's that for in terms of everyday life or even, you know, physics experiments is very, very small. Okay. So so the uncertainty so I'm going to be a little bit rough here in defining my terms, but in space-time geometry, there'll be an equation in a second, is basically, so it depends on how closely you look. Okay. So I mean, that's a normal thing. Like if I have a piece of paper, you know, if you look at it under, it looks nice and smooth. If you look at it under a microscope, you realize it's, you know, very bumpy and so on. Okay. So, so you get an uncertainty or a fuzziness that depends on how closely you look. And there's a formula for it, which you can almost guess what the formula is going to be because it involves quantum mechanics and general relativity. And general relativity is about gravity. So this formula will necessarily have Newton's constant in it. So I'll put a G. It also involves quantum mechanics. What is the constant of nature that controls how big quantum mechanical effects are? I've always got Rex and Sirish. I wonder if there's someone else who wants to tell me.
Planck's constant.
Say it again.
Planck's constant.
Planck's constant. Okay. Planck's constant. So that's your H bar. Okay. And then you can just ask, well, if I multiply these two things, I get some quantity, it has some units, and I want to get some thing which is unitless to get the importance of the effect. Okay. So I want to get something unitless. This is a trick that theoretical physicists use a lot, which is just matching units. You can solve a problem just by knowing what units your answer should have and what units your inputs should have. I don't know if Azadeh, you've done this kind of dimensional analysis with these folks, but it's a nice shortcut often to guessing what the answer is going to be. So I'm not going to go through, but this is a fun thing you can totally do on your own because you know what units Newton's constant has, you know what units H bar has, and you're trying to make something that has no units. And there's actually only one way to do that, which is if the size of the thing you're looking at is L, you have to put an L squared there. And then this thing still doesn't have the right units, but thankfully there's another constant of nature that always pops up whenever you talk about relativity. Do you guys know what that might be? A constant of nature that's very important in any kind of relativity? Yes, Rex?
C.
C, which is?
The speed of light.
The speed of light. Okay, so to make the units work, you've got to have C cubed. Okay? And in fact, you can rewrite this in terms of a length, which is called the Planck length. And the Planck length is just defined by that equation. And so basically, if you're looking at a size which is very large compared to the Planck length, then this ratio is very small. And then when you square it, it gets even smaller. So whereas if you look at a length which is about the same as the Planck length, so that this ratio is about 1, when you square it, you'll get something about 1. And that means you have huge uncertainty. That means that space-time does not look smooth at all. And when you calculate this is something very easy to do. Just if you don't know the values of the constants, just look them up and calculate this. And you get about, well, I'll just do the order of magnitude, about 10 to the minus 34 meters. That is a very, 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 very small length. Okay? For comparison,
would you give us a some idea what that length means? Means that at that length, what happens?
So at that length, so if L is 10 to the minus 34 meters, then this ratio is 1, which means that your space-time geometry is fully quantum. It's fluctuating the same way that an electron's position is fluctuating in an atom. Okay? So that's why this is an important length when you try to put together general relativity with quantum mechanics. Okay?
What does it mean in terms of gravity at that length scale?
Well, basically, okay, let me answer that in 1 second. So I first want to just make very clear that this Planck length is a ridiculously small distance. And so just to compare it to something, more everyday, of course, people are like 1 meter, like I'm about a meter in size, an atom, is about, like I said, like an angstrom. So an atom, which is small, obviously for people, an atom is much smaller than a person, but 10 to the minus 10 meters versus 10 to the minus 34 meters, that's 24 orders of magnitude, okay? An atomic nucleus is about 5 orders of magnitude smaller than an atom. So very small, but still very, very, very big compared to the Planck length. And in fact, if you look at what they probe in particle accelerators, they can probe distances that are much smaller even than an atomic nucleus, something like 10 to the minus 20 meters in these experiments. Still much bigger than the Planck length. So to answer Azade's question, what happens at the Planck length? What happens is that the energy that is in these fluctuations, because whenever you have fluctuations of something, there's some energy there, okay? And gravity itself responds to energy. And so basically you get this runaway out of control situation where the equations you would use to understand what's going on, if you tried to use quantum mechanics and general relativity together, just go bonkers, okay? Because you have these fluctuations in energy, and those fluctuations in energy are feeding back on the geometry. The geometry has fluctuations which have energy, and the whole thing just is a mess. You get equations that basically make no sense, okay? I think there was a hand raised.
Yeah, Soren has a question, and you're at 50 minutes into the talk.
Okay.
Yeah, Soren, go ahead.
What exactly particles would be at the Planck length?
So yeah, that's a great question. So so what we think is that when we talk about a particle like an electron, okay, so you could say, how big is an electron? Okay. And if you answer that with experiments, we know that an electron is smaller than 10 to the minus 20 meters. Okay. But we don't actually know that it's an actual point. And in fact, it really cannot be an actual point. A point being something that has 0 meters, exactly 0 meters in size. Because basically general relativity forbids that. If you had an actual point, then the density, the mass density would be infinite. And that is not allowed in general relativity. Okay? So you would actually get a little black hole, and the whole thing would be much more complicated. Okay? And basically, the short answer is we cannot make a theory that has actual point particles with general relativity. So the thought is, in fact, this leads me right to string theory, is that actually an electron, a quark, all of those particles that we think are elementary, when you look at them close enough, they are not actual point particles, but they're actually strings. Okay? So when you look at it when you look at a point through a sufficiently strong microscope, you see that it's actually a string. And we don't know how big, if this is true. So first of all, we don't know if it's true. This is a theory that has not been tested. But it works mathematically. So it solves this problem because the strings are bigger than the Planck length. So according to this theory, the strings would be somewhere in between. See, there's a lot of room in between this 10 to the minus 20 meters, which is, we know that electrons are no bigger than 10 to the minus 20 meters, and 10 to the minus 34 meters. You have 14 orders of magnitude to play with. 10 to the 14 is a huge, huge number. Okay, so there's a huge range of distances. So you make the string somewhere in that range. And because they're not actual points, you don't get this violent fluctuations on distances of the Planck length. Okay, to give you an example, like if you have a process where two particles hit each other and go off, or maybe they hit each other and they make two other particles. So in a particle theory, so that would look like this if I plot what's happening against the time direction. So I have a particle coming in, maybe a black particle coming in, and a red particle, and then a purple particle coming out, and a green particle coming out. Okay, this point where they meet is very singular. Okay, something very sharp is happening at that point. You have 4 lines that are meeting at a point. In string theory, what's going to happen is you're going to have 4 strings that are coming along, and then will smoothly join. So this is still the time direction. Sorry for the sloppy drawing. Let me get rid of this. And they will smoothly join and split. And there's nowhere in this process where you have anything singular, anything sharp happening, because everything has been smoothed out. You don't get these mathematical problems, and you actually get a theory that agrees with quantum mechanics and agrees with general relativity. Okay, that's the basic idea of string theory. I haven't told you why it works except for this little cartoon here. But I think I'll stop and ask for questions because I don't want to just talk to the
No,
end of it.
that's a good point to stop. Can I ask the first question?
Yeah.
Do these strings have mass? Do we know, or?
Yeah, so well, they have energy, and E equals mc squared. So and the energy is from they vibrate. So it's just an elastic piece of string that that vibrates, and it can vibrate in different ways. So actually that's why in this diagram I don't have like purple string and green string. It's just one kind, but the vibrations would be different. So an electron would be a string which is vibrating in a particular way, and a quark vibrating in a different way, and so on and so forth. And you can reproduce features of the physics of our world, the kinds of particles we see, with string theory, although no one has yet managed to precisely get all of the details on the nose, like all the masses of all the different elementary particles. No one has managed to predict that from string theory. Not yet.
Do they also interact in so they interact with this underlying space-time also and change that as well, right? I'm assuming.
Well, so this is where, I mean, like a photon is a particle, but it's also a wave in the electromagnetic field, and a wave in the underlying space-time is a graviton, which is a string. So there's nothing but, in string theory, there's nothing but strings. Everything is strings, okay? And so that's why you kind of don't have to worry about this. Basically, there's no Planck length in string theory. You just, below the string size, like there's nothing going on, essentially.
Okay. Pierce, do you want to ask your question and then I go to Soren?
Hypothetically, would you be able to change the way that a string vibrates so that it basically is a different particle?
Well, when it interacts with something else, if it's just by itself, it'll just keep doing what it's doing. But if it gets hit by another string, or if it emits another string, then yes, then the things going off would be different from what it started with. But again, there's nothing in string theory except strings interacting with each other, basically by processes that look like this.
Thank you.
Soren.
Do you have any theories on like what the strings would be made out of?
So some people say that's the question you're not allowed to ask in string theory. So we don't really know. So, but if, there's a different talk I could have given where you would actually give an answer to that question. And this is just a pure teaser, but this is something we've only realized in the last like 10 years in string theory, that there's a way of thinking about strings and gravity, which goes back to quantum mechanics, and specifically comes from this thing that I don't have time to explain, called quantum entanglement. So actually, there's a way to get to string theory directly from quantum mechanics. And there you would answer the question of what the strings are made of.
So they know a bit of entanglement. They know what entanglement is. We have talked about that.
Great. So if you have enough entanglement, basically in the right way, you basically get gravity out. So in the story I've been telling so far, we've been assuming that there's gravity and assuming that there's quantum mechanics, but actually you don't have to. You can just assume that there's quantum mechanics, that there's entanglement, and the space-time itself. You don't have to assume that there's space-time. It actually comes out of the entanglement. And this is the idea of the world as a hologram. So the whole world, the three-dimensional space and everything is just an illusion. It's a hologram which is created by this massive amount of quantum entanglement. And in that framework, you can actually say what the strings are made of. That's a whole other hour.
What do they made out of in one sentence?
There's just some like primordial stuff, some physicsy stuff that obeys quantum mechanics. And that's all you need to assume, basically.
Sirish, go ahead.
So are these like vibrations actual like physical vibrations, or they're more like a quality like spin, to where it has some sort of an energy along those lines?
Well, it's a vibration, but it does obey the rules of quantum mechanics, like spin, so that it's quantized, so that there are discrete energy levels, like in electrons of an atom or any kind of quantum harmonic oscillator that has discrete energy levels. And so that's actually why you don't have a continuum of different particle species, is that basically because of this quantization, one quantum level would be an electron, a different quantum level would be a photon. And of course, there's different directions they can vibrate in, like it can vibrate like this, or it can vibrate in some funny way like this or like this. And so, plus, I didn't even mention this, but in string theory, there's 6 extra dimensions of space that they can vibrate in. So there's a lot of ingredients, and that's why you get all these different kind of, particle species that we see. But they are quantized like spin, like energy levels of an atom, and so on. Yeah.
All right, very good. I'm sorry about this text. I can't turn it off. Any other questions? This was amazing. We probably need you for another like 4 more talks or something. But we know you're very, very busy. Thank you so much for coming. Do you guys have any questions? The last chance. Last chance. All right. Thank you so much, Professor Headrick.
Thank you, Azadeh. Thanks, everyone. It was fun.
So much. We appreciate you. Thank you for your time. And this was great.
Yeah. All right. See you guys.
See you guys.
Thank you.
Thank you so much. This was
Bye.
great.
Great.
Thank you so much.
Bye.
Bye. Thank you.
Bye. Bye, everybody.
Thank you.